Chemistry 20. This is our 6th lesson in the Diversity of Matter and Chemical Bonding unit. This is Bond and Molecular Polarity. In this lesson, we will recap electronegativity, bond polarity, then we will look at molecular polarity and how to determine the polarity of a molecule. Remember that electronegativity refers to an atom's ability to pull electrons closer towards its nucleus when in a chemical bond. When we talk about a nonpolar covalent bond, we refer to similar electronegativities between atoms, resulting in the even sharing of electrons. In this picture, we can see two hydrogen atoms sharing electrons. Both hydrogens have the same electronegativity, the same ability to pull electrons closer to their nucleus. Therefore, those shared electrons will be shared evenly right in the middle of the bond. Polar covalent bonds are when there's a significant difference in electronegativity between atoms, resulting in an uneven sharing of electrons. Those electrons are always pulled closer towards the more electronegative atom. In this example, we can see a bond between chlorine and hydrogen. Chlorine has a higher electronegativity. Therefore, it has a greater ability to pull electrons closer to its nucleus. The electrons in this bond will not be evenly shared. They will be closer to the end of the bond near chlorine. They will be closer to the pole of the bond, making a polar covalent bond. The uneven sharing of electrons in a bond results in a slightly positive and slightly negative side of the bond. If we look at this example, we can see a bond between hydrogen and oxygen. Oxygen has a higher electronegativity when compared to hydrogen. Therefore, these electrons will be pulled closer towards oxygen's nucleus. They will not be at the midpoint of the bond. They are closer towards oxygen. We know that electrons have a negative charge. Therefore, this side of the bond will then be slightly negative. That means that the opposite side of the bond has to be slightly positive. This can also be shown using the following symbols: slightly negative and slightly positive. Polarity vectors are also used to show the polarity of a bond, where the arrow of the vector points towards the more negative side of the bond and the tail points towards the more positive side. It's also important to note that polar also is referred to as dipole. Dipole meaning two different poles, a positive and a negative pole. Just like polar bonds, polar molecules also have a slightly positive and slightly negative side. Polar molecules are also referred as dipoles. In our example, we can see a molecule of H2O, where both bonds have a polarity vector pointing upwards. That means that the more negative side of both bonds is located closer towards oxygen. Oxygen also has two lone pairs around its nucleus. Therefore, this is going to be the more negative side of this molecule. As a result, the hydrogen side will become the more positive side. Nonpolar molecules, on the other hand, do not have a positive or negative side. They can be considered neutral. Determining molecular polarity. Step number 1, we have to determine the molecular shape of the molecule. Step number 2. Determine the polarity of each bond within the molecule. And finally, step number 3. Compare all bonds and the molecular shape to determine if the molecule is symmetrical or asymmetrical. A symmetrical molecule is nonpolar. This is when all polar bonds are counteracted by other polar bonds with the exact same strength, meaning they must be counteracted by the exact same bond. An asymmetrical molecule is polar. This is when all polar bonds are not counteracted by other polar bonds with the exact same strength. Example number 1. Draw the Lewis dot structure, determine the molecular shape, draw the Vesper diagram, and determine the polarity of NH2F. Pause the video and attempt this example. Most importantly, we have to draw a proper Lewis dot structure, which is represented here. We can then conclude that the central atom has 4 electron groups around it, here, 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 and here. This makes a tetrahedral geometrical shape. But there are 1 set of lone pair electrons on the center atom. Therefore, that changes the molecular shape to a trigonal pyramidal. We then have to draw the Vesper diagram. And we have to determine the polarity of each bond in the molecule. We can see that the polarity of the hydrogen-nitrogen bond points towards the nitrogen atom, meaning that is the more negative side of the bond, where the nitrogen-fluorine bond, the more negative side is towards the fluorine. We can see that not all bonds are perfectly counteracted in this molecule. And we also have a lone pair on the nitrogen, which is not counteracted properly by the fluorine bond. This is going to be an asymmetrical molecule, making it a polar molecule. Example number 2. Draw the Lewis dot structure, determine the molecular shape, draw the Vesper diagram, and determine the polarity of CO2. Pause the video and attempt this example. First, we have our Lewis dot structure, where we have a double bond between each of the oxygens and the carbon. We can then conclude that the center atom carbon only has 2 electron groups around it, making it a linear geometrical shape. And since there are no lone pairs on carbon, the molecular shape will also be linear. Our Vesper diagram will look the exact same as the Lewis dot. And we can draw the bond polarity vector arrows. We can see that the more negative side of each of the bonds is pointing towards the oxygen atoms. These are the exact same bond and are perfectly counteracting each other. Therefore, this is a symmetrical molecule. This is a non-polar molecule. Example number 3. Draw the Lewis dot structure, determine the molecular shape, draw the Vesper diagram, and determine the polarity of CCl3F. Pause the video and attempt this example. First, we have our Lewis dot structure. We can see that there are 4 electron groups around the center atom carbon, here, 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 and here. That makes a tetrahedral geometrical shape. And since there are no lone pairs on the carbon, that makes the molecular shape also tetrahedral. Therefore, we can draw our Vesper diagram, and we can put in our vector arrows. As we can see, each one of the bonds has a polarity that's pointing towards the outer atoms, meaning the outer atoms have the more negative side of the bond, whether that is chlorine or fluorine. Now, all of these bonds are counteracting each other, but not perfectly, and that's because they are different atoms. These chlorine bonds are not counteracted perfectly by the fluorine bond. Therefore, this is still an asymmetrical molecule. This is going to be a polar molecule. Just to recap molecular polarity, this is an excellent diagram to use. And what we're representing is that A is always the center atom, where X will be our outer atoms. So since if we look at a linear molecule, we have our center atom and the exact same atoms on either side, their bonds would be perfectly counteracted, making this molecule nonpolar. But the moment we change one of the outer atoms, for instance, we have X, but now we have Y, their bonds will no longer perfectly counteract each other, so this molecule would now be polar. This also goes for trigonal planar. When we have our center atom and we have three of the exact same atoms bonded around it, it is going to be nonpolar. But the moment we change one of those atoms from X to Y, they will no longer counteract each other, making a polar molecule. And again, this also applies to tetrahedral. When we have A and we have 4 X atoms bonded around it, we have a nonpolar molecule. But the moment, again, we change one of the X's to a Y, the bonds will no longer counteract each other, and this molecule will be polar. It's also important to note that X or Y could also apply as a lone pair of electrons. And what we will realize is when there's a lone pair of electrons around a center atom, the molecule will always be polar. Moving forward, we will explore the concept of intermolecular forces.